Hello, and welcome to today's webinar on flow, level, temperature, and pressure instrumentation, focusing on level measurement in hazardous areas, and brought to you by Control and MTS Sensors. I'm Paul Studebaker, Editor-in-Chief of Control Magazine and ControlGlobal.com. Before we begin our presentations, there are a few housekeeping issues I'd like to review. On your screen, you should see several primary sections. The upper left, or audio control section, allows you to adjust the volume of this presentation. Just hover over this section until you see the audio volume control and adjust the volume to your preference. To the right, in the largest section, is where today's presentation slides are displayed. Under the slide window, you'll see a chat section where you can chat live with fellow audience members. At the left of the slide window is the questions and answers box, where you can type a question for the presenter at any time during today's webinar. We'll get to as many of these questions as we can during the Q&A session following the presentations. If we're not able to get to your question today, or if you have a question after the webinar is concluded, we'll respond later by email. The handout section at the bottom left contains links to several resources, including the full set of speaker slides, some application specification data sheets, a guide to level measurement in oil and gas terminals, and a paper describing installed cost considerations. At the bottom of your screen, you should see icons for additional features. By hovering over each icon, information about the icon will be displayed. If you have any technical problems, you can type in your question or concern in the questions and answers box, and one of our technical engineers will assist you. If you need a better view, you can enlarge a section by clicking on the box in the top right corner of the section next to the X. If you accidentally close out a section, you can get it back by clicking the Restore button at the bottom of the screen, located to the left of the icons. This webinar will be archived, and we encourage you to direct coworkers to the recorded presentation. At the end of the presentation, we'll ask you to complete a very brief survey to give us the feedback we need to improve our webinars. Our main speaker today is Lee Aiken, Global Market Segment Leader for Liquid Level at MTS Sensors. Along with 12 years experience in technical marketing and level gauge development at MTS, Lee has a bachelor's degree in electrical engineering, an MBA from North Carolina State, and participates in American Petroleum Institute meetings for Chapter 3 tank gauging. But before I turn the controls over to Lee, let me talk for a few minutes about dealing with electrical equipment in hazardous areas. A hazardous area is defined as an area in which an explosive atmosphere is present or may be expected to be present in quantities such as to require special precautions for the construction, installation, and use of potential ignition sources. An area may be hazardous due to potential leaks or the presence of combustible gases such as hydrogen, or vapors such as hydrocarbons, or powders of many types from flour to fine metals. All these are potential fuels for combustion, resulting in a fire or explosion. At its most basic, an explosion requires the presence of three components: fuel, an oxidizer such as air, and a source of ignition. Typically a spark or hot surface. Pardon me. Remove any one of the three and the explosion won't happen. Fuel-air mixtures aren't automatically explosive and are characterized by a lower and upper explosive limit. A mixture too rich with fuel or lean of oxygen won't explode, and even at the fuel-air ratio most favorable for an explosion to occur, a certain minimum amount of energy is needed to ignite an explosion. Electrical and electronic equipment in hazardous areas must be engineered to prevent it from providing an ignition source of sufficient energy to spark an explosion. The three most common methods of protecting a hazardous area from electrical spark ignition are to use explosion-proof housings, to purge the electrical enclosures, or to use electronics that are intrinsically safe. Explosion-proof or flame-proof containment methodologies rely on heavy enclosures and precisely machined flanges to contain and cool any explosive gases before they can propagate to the surrounding area. Purged enclosures are positively pressurized with air or a non-oxidizing gas such as nitrogen to prevent an explosive atmosphere from entering the enclosure. Intrinsic safety technology is engineered to limit electrical and thermal energy to levels incapable of causing an explosion. Other less commonly used segregation methods include encapsulating the electronics in resin, immersing them in oil, or burying them in sand to keep the electronics and the energy a fault might generate away from air and fuel. Intrinsic safety recognizes that the potential for a circuit to generate an arc or spark is determined by the circuit's ability to conduct and store energy, then suddenly release it. By limiting the ability of a circuit to conduct and store energy to a level below a hazardous area's minimum ignition energy, it's possible to prevent an explosion even if a short or other fault occurs. Intrinsically safe circuits typically use barriers at the transition between the safe area, where voltages and currents are unlimited, to the hazardous area. To prevent a spark, energy must be limited, so intrinsic safety can only be used with low-power circuits. Typical barriers use either Zener diodes or galvanic isolation. Zener barriers, shown at the top, shunt excess current to ground until a fuse gives way. Galvanically isolated barriers are typically more expensive, but grounding is not needed, so they are comparable in installed cost and offer other accuracy and noise rejection advantages. I'll now turn our presentation over to Lee Aiken. Lee?
Thanks, Paul. So I'd like to extend my welcome to everyone just like Paul did, and then we're going to start walking through the rest of the presentation. There's three main sections to the rest of the presentation we're going to walk through. We're going to take a little bit more of a look at some of the hazardous area protection methods. We're going to take a look at liquid level technologies, and then we're going to take a look at the markets and applications where some of the common level technologies are used. So Paul did a very good job of covering a lot of the information on the hazardous areas. So just like he said, you have the fire triangle. You need all three of these elements: a fuel source, oxygen, and an ignition source to actually create a flammable fire or an explosion. And what we're doing here with these different protection methods is we're limiting this. The different protection methods, each one removes one of those three legs of the triangle and keeps that explosion or that fire from occurring. So Paul went through and talked about the definition and what a flame-proof, explosion-proof is. If you're not familiar with the terms, a lot of times you'll hear these two terms used interchangeably. For the most part in the U.S., the protection method is referred to as explosion-proof, whereas the same protection method is referred to as flame-proof in Europe. And then the rest of the world goes off of one or the other, just depending on usually who's doing the engineering effort. But these are synonymous with the same kind of protection method where you're looking at containing the explosion. So you're not preventing it from occurring, you're just containing it if it does occur so it doesn't propagate through the rest of the plant or the installation. So on this side, we're showing what a typical level transmitter installed with an explosion-proof installation looks like. So you have the level transmitter, and then you have the rest of the system. One thing to make sure to point out here is that when we talk about these kinds of protections, we're not talking about just the single device itself. We have to talk about the entire system and how the entire installation is going to occur. So the device, in this case the level transmitter, it has to be connected using explosion-proof conduit, seals with poured seals or seal-offs, any of the fittings or junctions themselves. All these things must carry an explosion-proof or flame-proof rating, and it must carry the same rating as the area where it's going to be installed. So a lot of customers run into problems where when they're doing these kinds of installations, they don't look at the entire system, and you have to make sure that your system is going to match the electrical code for that country or where that installation is occurring. So in the U.S., the example would be the NEC, or the National Electric Code 500 or 505, has a lot of the information about the details of what needs to be done for this entire installation to meet the codes and meet the approvals. Now, with each device, you also have specific conditions of use from the manufacturer. And the manufacturer is responsible to provide that to the end users to make sure that they're able to install the device correctly, because even though the devices are very similar, there are small differences that will make a difference as far as whether or not that installation is safe. So you need to make sure you take a look at the electric code that's responsible for your area, and also take a look at the specific conditions of use for that device. And once you do that, then you can have a safe system. So for intrinsic safe or intrinsically safe, this is on the opposite end of the spectrum from the explosion proof, whereas before you were trying to contain the explosion, here you're preventing it. You're not allowing enough energy into the hazardous area where that spark is hot enough to actually ignite the liquid or the gas. Again, just like I talked about with the explosion proof, it's about the system installation. So Paul mentioned you need to have the safety barriers. That's one key element. You also have to take a look at the cabling and then what's referred to as the entity parameters. So this is going to be the rating of the device, and you need to match the device with the safety barriers, and then you need to make sure when you include the cable, usually looking at the capacitance and the inductance of the cable, that overall the system itself still meets the guidelines. So you need to make sure all those things are done and matched up correctly, and for the most part, the intrinsically safe installations require a lot more design work. They're easier to physically install because you don't have all the explosion-proof components, but there's a lot more thinking that has to go on at the beginning to make sure everything's matched up. You also do have some additional regulations around the cabling. You do not want to have intrinsically safe rated cable where you're regulating the energy in the cable next to any cable that's not intrinsically safe. And you also typically want to limit your low voltage cable from running next to your high voltage cable, so you don't have any energy bleeding over from one cable to the next due to EMC and EMI. Now, one common misconception that I hear a lot when talking to customers is if I put a safety barrier on the device, that makes it intrinsically safe. And this is not true. The safety barrier will limit the amount of energy that goes down the cable to whatever device is connected, but that doesn't mean that that device itself is able or has been rated as intrinsically safe. Each component must be looked at to make sure there's not any stored energy that could be released and cause a spark that would ignite the atmosphere. So you have to be very careful and look at the overall system, each component of the system, and not just think that a safety barrier by itself will give you a rating. The other difficult part about the hazardous area ratings is all the different terminology and the codes and everything that goes into marking the product. This can be very, very cumbersome to learn. It also, as the standards get updated, the information gets updated. And then the other part of this is there are differences between the different approvals, the different ways you mark it, and everything else. So on a standard hazardous area marking, you have the top 5 points are generally what's on the marking. So the first two, your group class and your zone division, which these are roughly the same thing, it just depends on which approval you're looking at. These items are trying to describe the physical location of where either that device is going to be installed or the rating of that tank or that area of the plant. The next one is going to be your gas group. So here you're trying to describe the amount of energy that gas or that liquid has stored inside itself. So there's typically 4 main ratings here, and they're different depending on which approval you're looking at. If you're looking under the division concept, then you're going to be looking at a group A, B, C, or D, whereas if you're looking under the zone concept, you'd be looking at groups 2A, 2B, 2B plus H2, or 2C. The ratings are all trying to describe the different groupings of explosive liquids and gases and how much energy is stored, because that determines either for explosion proof, for how strong your housing or your containment must be, or for intrinsically safe, how small of an amount of energy you can have inside the device. So there are very large differences depending on which character or which letters are chosen. The fourth part is looking at the temperature. So this is the surface temperature of that device under fault conditions. So most of the time when you see these have some kind of rating as far as T1 through T6. And each one of those corresponds to a different temperature or surface temperature of that device. Usually this is not the standard surface temperature of that device, but this is going to be under fault conditions where something has shorted and now the device has heated up. And you want to make sure that this matches to the liquid or the service that this is being placed into, because you don't want the surface temperature of your instrumentation to exceed the ignition point of the liquid or gas where it's being used. The fifth part of it is called the equipment protection level. This is newer to the approvals, and you may see devices with this marking, you may not see them. It just depends on how recently that device has been approved. It's a try at defining the relative safety of the different protection methods. So a few slides back, we looked at a list of, say, 10 or 12 protection methods. As far as the standards are concerned, not all of these protection methods have the same protection level or safety rating. So they're labeled as far as a GA, a GB, or a GC protection level. And those would be for the gas groups. Same thing, DA, DB, DC for dust. And you have intrinsically safe, which would be a GA rating, saying that it has a very high level of protection. And then you would have a GB, and this would be your explosion-proof or your flame-proof level of protection. Since the intrinsically safe is preventing the explosion, it's considered safer and given the GA rating, whereas the explosion-proof, flame-proof is just containing the explosion, so it gives it a GB rating. So we're going to take a look at some of the examples. So before we dive into that, a lot of people see these and don't really understand what the zones and divisions are. As I mentioned earlier, this is a breakdown of the location. And for the location, we're looking at how often or how likely it is to have a presence of that hazardous area. So how often would you possibly have a liquid or a gas that is flammable or explosive in that area? Now, there is not a definitive standard that states this is how it breaks down, but this is just a general guideline here. So if 10 hours or more per year, you would consider that a Division 1 area, and between 1 and 10 hours per year, you're looking at a Division 2 area, and less than 1 hour per year, you're looking at a safe or not classified area. Now, this is the division concept, which is used in the U.S. and Canadian approvals. And then next to it, you can see the zone concept. The zone is used much more extensively under the ATEX or the European approvals, and now they've also started to migrate over to the U.S. and Canadian approvals. With the zone concept, you have 3 different steps instead of just 2 with the divisions. So you have Zone 0, which is 1,000 hours per year, or typically viewed at a constant presence of the hazardous area. You have Zone 1, which is between 10 and 1,000 hours per year. And then you have Zone 2, which is between 1 and 10 hours per year. Now, Zone 2 and Division 2 line up, but it's not the same approval. You cannot use those two interchangeably. The next part is actually looking at some of the example markings, and we're going to start with the division concept for the U.S. and Canada. So here it starts by writing out the name of the protection method. So here we have explosion proof, and then we have Class 1, Division 1. So we now know the location. We have the gas groups. So for this particular example, you have groups A, B, C, and D. So you can use it at any of the different levels. If you only had group C, D written, then you would only be approved for use in C and D, and it would not be approved for use in A and B. With the division concept, the group A is the most stringent level. And then the last part of it is you have the temperature code. Now we're still using the U.S. approval, but we're taking a look at the zone concept. So it looks a little bit similar, but also quite a bit different. So we start with the same class distinction, but now instead of the divisions, we have zones. So we have Class 1, Zone 1. And then with the zone concepts, you typically see next this EX marking. All the other approvals use an EX. The U.S. approval uses an AEX. This is how you're able to determine that it's a U.S. approval. Then next to that is going to be the protection methods. Now here we don't write out the protection methods. We have different letters that signify the protection method. So the little d signifies the flame-proof approval, and then the little I and the little a signifies the intrinsically safe approval. The next part is the gas groups. So here, since we're under the zone concept, we're no longer A, B, C, and D. We're 2A, 2B, and 2C. And just because it has to make life more confusing, the zone concept and the division concept actually go the opposite way with the lettering. So under the zone concept, the group 2C is actually the most stringent approval. So for zones, you have 2C being the most stringent, and for divisions, you have group A being the most stringent. The next part is the temperature code, and this is the same as we saw in the division concept with our T5 marking. We now go over to the ATEX and the IEC approval. So the base part of this approval looks very similar. We start with the EX. Then we have the protection method showing the D and the IA. We have the gas group with the 2C. We have the temperature code with the T5. And we have the equipment protection level, GB. So as I said earlier, the GB lines up with the flame-proof or the D approval. And then you can see inside the brackets, you have the IA lining up with the GA. Now for this specific approval, it's written slightly different than normal approvals. So this is saying that the instrumentation itself has a flame-proof rating, and then the brackets signify that it has an output that is intrinsically safe rated. So there are a lot of caveats to how these are written, so you have to be very careful if you see more than just one protection method shown, or if you see brackets, or if you see forward slashes or backslashes. All those things are breaking the approval apart differently, and it can mean different things. So you always want to make sure you can take a look at the approval and then take a look at the manuals and the certificates that come with it. And if needed, definitely talk to the manufacturer so you can understand what their approval is and whether or not it applies to the area or the application where you're looking at using it. One last part around the example markings is going to be for ATEX. ATEX adds some additional marking to its approval. The first part is the CE marking. This is required for sale in the European Union. It's basically outlining that you have done specific EMC, EMI testing, specific safety testing, and that you're certifying this product as being safe to go into the European market. The next part of that, here shown as 1725, is the number of the notified body. So this is the agency that you went to, or the manufacturer went to get the approval. So on the ATEX approvals, you know specifically that this is the place that issued the certificate, and then you can go and take a look at those certificates. Next to it, you have the EX marking. This is a standardized marking that's used on all ATEX products. And then before, we had it written out where we had Class 1, Division 1, or Class 1, Zone 1. Here, we're still writing out, instead of class, we have the group. So you either have the single I for mines, or you have the 2I for other than mines. And then next to that, you have the zone classification, but instead of written Zone 0, Zone 1, Zone 2, they write it as a category. So you have Category 1, 2, 3, and for whatever reason, Category 1 lines up with Zone 0, Category 2 with Zone 1, Category 3 with Zone 2. And then the last part of it is we have a designation as far as if this approval is for gas with the letter G, or for the letter D for dust. So a lot of characters, a lot of letters, a lot of information. All this is contained within the marking on the product, within the certification for the product. Again, this can be very confusing, very cumbersome. Make sure you talk to the manufacturer, and they can help explain exactly what the approval is on that product, and they should be able to offer guidelines as far as whether or not it's suitable for the application you're looking at installing it in. So that's it for the hazardous area markings. The next part we're going to do is take a look at the different, or 3 of the common liquid level technologies, and we're just going to run through some information about them. So the first one we're going to start with is magneto-restricted technology. And then this is just a little slide showing some information about it. And then the next part is going to be a video illustrating how it works. So with magneto-restricted technology, it is a float-based technology. So we have a float around a pipe, and inside of that float is a permanent magnet. What we do is we interrogate the element. So you have a sensing element that runs down the entire length of the pipe. It's interrogated with an electric pulse, and that pulse creates a magnetic field around the element. That magnetic field interacts with the magnetic field of the permanent magnet, and it generates a twist coming back up that element. So you have the initiation of electrical pulse, and you have a return twist, and you do a time of flight. It looks like the video stopped, so we'll change slides back. So now you can see the electrical pulse, and then you see the return pulse. And again, this is a time of flight measurement. It allows it to be a very accurate measurement given the way the technology works. This technology is not only used in level measurement, it's also used in other industries to do position measurement and other kinds of applications. Here's just a picture of a standard magneto-restricted level transmitter. A list of some of the companies, in addition to MTS, that manufacture magneto-restrictive sensors. And then the pros and cons of a magneto-restrictive sensor. So the first pro is the ease of installation. Since these units are self-contained, they're not relying on anything that comes external from the device, that they are easy to install. You can just drop them in from the top of the tank. This can be done while the tank is in service, as long as it is not a pressurized vessel, and it's pretty easy to install. The next benefit of this is that you get a combination sensing. So you're not just doing a single level measurement off of this. You can actually measure multiple levels. So the easiest example is doing oil and water. So if you have an oil storage tank, a lot of customers like to also measure for the presence of water at the bottom. They don't want to have water in the tank, and they don't want to accidentally sell someone water instead of oil. So that's a standard application where you can use the 2 different level measurements. The other part of it is you can combine a temperature measurement. Since the level technology is in contact with the liquid, you're already able to sense the temperature of the liquid without having to add a secondary device. And then the fourth part of it is doing a volume calculation based off of a strapping table or a spherical volume, so you can get product level, interface level, temperature, and volume all from the singular device, hence the 4-in-1 measurement. As I mentioned earlier, the technology is contained, so the actual sensing is done from inside the pipe. So if you have environmental conditions such as vapors, or it could be gas blankets, or if you have foaming, you have dust, you have changes in the dielectric constant of the liquid, if any of these variables are changing, it does not affect the magnet-restricted technology. Also, it has a very high degree of accuracy. Depending on the length and the manufacturer, you're looking at somewhere for shorter stuff, a 0.5 millimeter accuracy, 1 millimeter accuracy. It just depends on exactly which one you're looking at. The downside of it, a lot of press right now about not wanting to have level measurements that are in contact with the liquid. So this does go against that current trend, but as I stated previously, because it is in contact with the liquid, it's able to give you the additional ability of doing a temperature measurement. Whereas for if you were using a different technology, you could have a non-contact level transmitter, but then right next to it you would have a temperature transmitter that would be in contact with the liquid. And then the last con would be the lack of awareness of the technology. The technology has been out for, say, over 40 years, but it's still not a really well-known technology. The next technology we're going to take a look at is the guided wave radar. So here you have a radar transmitter that has a guide, typically either a pipe or a flexible cable, and it uses that pipe or cable to guide the microwaves that it's sending out. This way it's able to have better performance in certain applications than the standard through-the-air radar. So it sends it out, and then as it hits the different liquids or the different mediums, depending on the dielectric constant of that medium, it sends a return pulse back up to the electronics. So the electronics use this to do a time of flight measurement to determine how far away the liquid is. Guided wave radar is able to do 2 different levels, so it can do a product level and a interface level. There are restrictions around what the difference in dielectric constants have to be and some other details, so you have to make sure that before you purchase this for an interface measurement that you take a look at the details of the specific guided wave radar that you're looking at purchasing. Not all of these are capable of doing interface, so you just need to make sure you're looking at one that can do interface. The next one is just taking a look at the common manufacturers. So those are up here. And then I do have to apologize. While making the slides, I did make an error. So what's shown here is a through-the-air radar unit and not a guided wave radar, but the manufacturers are still the same. The pros and cons of the technology. So you have the through-the-air radars, which can be high-accuracy devices. And then you have the guided wave radar, and as I stated earlier, since you have that guide to focus the radar and the microwaves, it's able to perform better if you have light foaming or dust in the tank because you have focused the beams. It is a lower cost system, especially compared to the high accuracy through the air radars. The downside, so with that high accuracy for the through-the-air radars does come a higher price, and that may be a downside depending on your application. You do have a lot of specifics around the mounting of these units, where it's mounted, how it's mounted, the angle at which it's mounted. The other part of it is you do have to do a lot of calibration and setup, especially for the guided wave radars. If you purchase one of the units that can be cut to length, then you end up having to do the calibration in the field. So mechanically you're able to cut it to the length of the tank, but then you do need to go in and work on the electronics to make sure that you have it tuned for that specific application. The other con would be that you're not able to measure the temperature. because it's not included with that device. And then also with the guided wave radars, you do have a blanking distance at the top and bottom of the tank. The third technology is going to be the ultrasonic. So again, you're looking at time of flight measurement, very similar to the guided wave radar, but instead of using microwaves, now we're using sound waves. So those waves go through the air, intersect with the liquid, and then they come back. Some of the common manufacturers for the ultrasonics. And again, for all three of these technologies, these are not the only manufacturers. There are a lot of other manufacturers around the world. This is just a short list of some of the more well-known manufacturers. The pros and cons. The biggest pro about the ultrasonics is that it's the lowest cost, non-contact level measurement technology out there. And since it is non-contact and nothing has to be done to it, you can get a very short lead time on these units. They've been going out and doing a lot of replacement of other technologies. Now the downside, they are limited as far as being able to work in harsh environments. So when I say harsh environments, this is going to be anything that creates a barrier between where the ultrasonic sensor is mounted and the liquid that it's going to measure. So since it's just pushing sound waves through the air, anything that changes the landscape of the air as far as foam, dust, mist, steam, different layers of gas, all those things are going to affect the ability of those waves to propagate and provide an accurate level measurement. The setup can be complicated, so you do get different false echoes from interference in the airs. And then the last point would be that you have a minimum distance at the top or the bottom that you are not able to get either the accuracy or any measurement out of. So just common things just to be careful of when you look at selecting the level technology. So quick comparison here. So you have the three different technologies, magnetostrictive, guided wave radar, and ultrasonic. So the guided wave and the magnetostrictive are contact technologies, whereas the ultrasonic is not. All three can provide a product level. The interface level, the ultrasonic cannot do this. The magnetostrictive can, and the guided wave radar can, as long as you meet the right conditions. And then for temperature, the magnetostrictive can provide temperature, whereas the other two technologies cannot. And then the volume output, the magnetostrictive can, the ultrasonics, I have not seen any of the advertising providing volume. Guided wave radar, there are some models out there that it can also do the strap table conversion and provide a volume out. So if you're looking for that feature on the guided wave radars, make sure you look very closely and select the correct one. Some of the common things that I have questions from customers about, ease of installation. So I talked about this a little bit. For magnetostriction, you can just drop it in the tank. You're not highly concerned about the mount. For guided wave radar and for ultrasonics, you're very concerned about the mount because you want to have a nice perpendicular mount to the tank, so you can just shoot either the microwaves or the sonic waves straight down to the liquid and back. There's the accuracy ratings for all three. Now I will tell you the accuracy can differ from one manufacturer to the next. This would just be the average of what I see in the industry. But do not assume that just because you're buying a specific technology that device is going to provide that level of accuracy. Make sure you take a look at the specifications and talk to the manufacturer. And then the last 5 points here, taking a look at the differences. Some of this is mainly how it works or how that technology works. So for vapors, for gas blankets, gas layering in the air, the magnetostrictive is not effective, the guided wave radar is not, but the ultrasonic is. For foaming, magnetostrictive is not affected. Depending on the guided wave, it can be affected, and then the ultrasonic is affected. Dust, guided wave, and magnetostrictive are fine, ultrasonic is not. Specific gravity, if you have large changes in specific gravity, since magnetostriction is a float-based technology, you can have issues. For the guided wave radar and the ultrasonics, they're based off of differences, so they would not have the same issue with specific gravity. Viscosity, ultrasonic is a non-contact solution, so it does not care about the viscosity of the liquid, whereas for magnetostrictive and guided wave radar, you can have issues depending on the viscosity of the liquid. So taking a look at some of the markets that hazardous areas for level measurement are used. So you have the oil and gas market throughout that. So the upstream, midstream, downstream, all different parts of the market use these technologies. You also have the chemicals. You can do that as the standard chemicals, your specialty chemicals, your petrochemicals. There are other markets out there that use hazardous area approvals, but I would say that these are the main ones. So some of the applications within this. So when you're looking for an application, or you have your application and you're trying to specify the level sensor, these are the main points that need to be known. You know, we need to know about the liquid itself, you know, the density of the liquid, the dielectric of the liquid, the viscosity. We need to understand the tank. You know, what's the temperature in the tank? What's the pressure? How tall is it? How large is the opening on the tank? And then, you know, the other parts would be the approvals. What is the hazardous area approval for that tank? And then the last part would be what kind of output? What protocol do you want used on that tank? So here at MTS, what we came up with was what we call an application data sheet. This is just a little tool that's used to help gather all the information. Our sales team, customers, anyone can go and download this and they can fill it out, put all the information down on paper, and then that helps the manufacturer understand the application and provide the best guidance of, yes, this is a good fit for our technology, no, it's not a good fit, and this is just a tool to help collect all that information. So we have a few different applications we're going to take a look at real quick. So one application is the bulk storage of refined fuels. So here you're talking about fairly large tanks, and this is just storing fuel. Typically, the refined fuels is going to be exiting from the refineries, going out on the pipelines or tanker ships, making their way to the in-use destinations. So here, having the ability to measure very accurately is key for the customers. They also, since they're doing inventory management, because these tanks can be a couple million gallons of fuel in them, they like to have the volume conversion, and they also like to have the temperature measurement. Similar to the refined fuels, you have the bulk storage of the crude oil, and this would be going more into the refineries and before you have the finished product of the refined fuels coming out of the refineries. Very similar application as the refined fuels. The main difference here is that you're not as concerned with a interface measurement or a water measurement at the bottom of the tank, because a lot of times you don't have the separation between the crude and the water that you would between the refined products and the water. Next one would be looking at the LPGs. So this would be your liquefied petroleum gases. So such things as propanes and butanes. Now the difference here would be that these are all pressurized vessels. So you do have pressure within the tank. You cannot just go and open the tank. So when you're looking at a level transmitter for this, you want to be able to take a look and understand what is the field service, what's the repairability of the device. You do not want to have to take one of these tanks out of service just to do a common repair on a device. So you want to see and find a technology and a specific manufacturer that allows you to replace, for example, your electronics due to a lightning strike. If you have to take the tank out of service to do that, then that's not going to be a very good fit for this application. Sump tanks are another one. So this was usually just a runoff tank. So here in the picture, it's a truck rack where they're loading from the bulk storage tanks, usually along a pipeline to the tractor trailers that are going to take it to the gas stations. You do get spills and runoff, so they have a tank that collects all those spills, and it's typically referred to as a sump tank. In that tank, you end up with a mixture of fuels. You can have gasoline, you have diesel, ethanol, water. So you have to look here for a level technology that's able to measure all those different liquids within that application. Alkylation, so this is part of your downstream, your refinery. It's a step within the blending process to help boost the blend rating. Here within an alkylation tank, you're actually looking at 3 liquids in the tank. So both of your measurements are an interface measurement. So you need to be very concerned about whether or not the technology is going to be good at measuring interface. Here would just be general acid tanks, so looking at storage or the creation of different acids at chemical plants. So one part of this is you do need to be careful with the chemical compatibility between the liquid and the device being put into service. And this is not just for contact devices, but also non-contact devices. You do get different steams and vapors, and you can still have the same kind of corrosion if you're not careful. But again, these would be bulk storage tanks, very similar to the refined fuels and the crude oil. Last application we're going to take a look at is blending. So in blending tanks, referred to also as reactors, you're mixing or trying to separate different liquids, and during this process you can get reactions. This can generate foam, this can generate heat, a lot of things that can happen. A lot of times you also have agitation or mixing within the process. So now you're looking for a level technology that can provide a very high level of performance in that harsh condition. So again, make sure when you're talking to any manufacturer trying to specify level equipment that you fully explain your application and what's inside of it and what your process is. And you know, reputable manufacturers will be able to tell you this is, yes, a good fit, this is something we could do, or no, this is not. Okay, and then the last slide is just my information if anyone needs to get in contact with me for more questions. And then I'll turn it back over to Paul for the Q&A.
Well, thank you very much, Lee. Yes, we have some time for questions and answers. We have several very interesting questions that have come in. While we start answering them, please feel free to continue to send questions. Anything we don't get to during our presentation, we will answer later by email. So Lee, our first question says, you described several different ways to protect equipment in hazardous areas. Which hazardous area protection method is the best for a liquid level transmitter installation?
Okay, so there's not necessarily a single best protection method. Most of the time it's up to the end user to define what's the best method for their application and for their process. A lot of people have different opinions about what they believe is the best one, but you really need to take a look at your installation and what the installation cost of those different protection methods would be. You may see we're doing an intrinsically safe installation on this specific tank, this specific application. That could be the best for one application, whereas maybe for the next application, the explosion-proof, flame-proof methods are better. So it really comes down to the end user about their preference, and then usually also about the application and if something lends itself better to one or the other.
Okay. Our second question, does it matter which approval agency issues the certificate?
We get this question a lot, and especially now that more of your approval agencies are starting to offer approval in different regions. And this is new, whereas before, so for Canada before, everyone had to go to CSA for the approval. They were the only agency in Canada. Now there's multiple agencies able to issue the certificates for Canada, and a lot of manufacturers are going out and getting approvals from different agencies based upon the fact that more agencies, now that there are more agencies out there, it helps shorten the timeline for getting approvals. So we've had a lot of customers come back and say, well, you know, this isn't from CSA or this isn't from UL. You know, is it still safe? Is it still usable? And the answer is yes. As long as you're getting a certificate from one of the recognized bodies. So in the U.S., it would be a NRTL, a nationally recognized testing laboratory, or under ATEX, it would be called a notified body. As long as you're getting a certificate from one of these agencies that is recognized and approved, then there is no difference in that certificate in the safety of that product.
Okay. We have a question about level measurement for a wood batch digester. Have you encountered such an application?
A wood batch digester. So as far as MTS, we work in pulp and paper mills on a lot of different applications. Some are on the level side, some are on the positioning side. We have done, on the level side, what we have done, I do know we have done measurement within the black liquor tanks. I do not think that we have done anything with a wood batch digester. So I'm not sure about that specific application.
Okay. Here's everybody's favorite question that somebody asked. How should I determine which liquid level technology is best for my application?
Well, so the unwelcome but simple answer is that there is not going to be a single technology that is always best for all applications. Really what you need to do is take a look at and understand what are you trying to accomplish with the level measurement in your tank. What is the specific purpose of it? Are you concerned about just overfill? Are you concerned about inventory? Are you concerned about accuracy? Do you need temperature? How many liquids are in the tank? And if you can write down all the specifics about the tank, then you can start looking at different technologies and understanding which technology lends itself best to that type of application. There is not a singular answer for this to say, oh, well, if you're doing such and such measurement, you should always go with this technology. Different manufacturers will try to tell you, this is the best technology, you should always use it, but that's not always the best approach.
Okay, I think you answered this next question, which is my company wants to standardize on a single technology. What's the best liquid level technology to standardize on? So.
Yes, we've encountered this question too before. There is no one technology that you can standardize on because not all the applications are the same. And what we try to help customers understand is that the cost savings of standardization, they're going to go away and be given back to, losing money because you're buying a high performance level sensor for a small tank that doesn't need high performance. Or you bought a low performance level sensor for a tank where you need high accuracy. So we've talked to a lot of customers about standardization, and we don't recommend it unless you have a single process at your facility and all the tanks are the exact same. If you're lucky enough to have that situation, then you could standardize. But for most customers that have some tall tanks, some small tanks, some are storage, some are process, some are incoming chemicals. Just due to the variance in all the different applications, it's really not beneficial to try and standardize, again, because you end up putting the wrong technology that's not the best fit into a tank where you could get better performance.
Okay. Well, that brings us to the end of the questions that have been submitted. Audience, bear in mind that you can still submit questions and they will be answered by email if you have something very specific or a strange problem. Definitely send in a question. I'd like to thank our speaker, Lee Aiken, our sponsor, MTS Sensors, and all of you who joined us today. This webinar has been recorded and will be available for on-demand viewing. The slides and assets from today's presentation will also remain available for on-demand viewers in the handouts area. So now, did you like our presentation? Please let us know your thoughts by answering our brief survey that will appear on your screen shortly. Your candid answers are not only appreciated, they help us craft our future events. Thank you for your attendance and have a great day.